On Friday, we left off with mechanical energy. We had talked about nuclear and solar, and we had talked about chemical energy. We talked about electricity and magnetism as forms of energy. Okay? And now we need to talk about the most important one for this course, and that is mechanical energy. Mechanical energy is possessed by anything that has the ability to do physical work. Okay? So if something has potential energy, that potential could turn into kinetic and do work. If something is moving, it has kinetic energy and could do work. Right? So in those cases, those are the two basic types of energy within the form of mechanical energy. Okay? And we talked about that with I used my water bottle as an example of that on Friday. I said, if it's on the floor, does it have any energy? No, it can't do any work from there. It can't fall any further, it's not moving, it has no ability to do work. Okay? But if I pick it up and throw it, I'm not going to, okay? But if I did, then it would be moving and it would have kinetic energy and would then be able to do work. Okay? Similarly, now that it's on the desk, does it have energy? It does. It has mechanical energy because it has potential energy. Okay? Why does it have potential energy? Because it could fall? Yes. How did it get it is the way I should have phrased that question.
Because we did something with it.
Yes. I did do something with it. And it starts with W. 4-letter word that we all hate doing. Work. Yes. Okay? I did work. Okay? And work and mechanical energy are very closely related. Right? The only reason that this water bottle has energy is because I took it from the floor. I burned a couple of calories, okay, doing that work. I gave it energy because I did work on it, okay? And I do work on it if I throw it and make it go fast, okay? Anytime you exert a force and you make something move through a distance, you're doing work, okay? You're transferring energy. Any question?
I did.
What's that?
Oh,
Okay. All right, the little thing there on the right, Newton's cradle. Okay, Newton's cradle is a perfect example of mechanical energy, and it was what Newton used to explain the nature of energy back in his day. Right? Unfortunately, people did not understand his genius at the time and his explanation of why this thing worked the way it did. Okay? All they saw was somebody take a ball and move it away from the others, and when they let it go, it would hit the others, and the one on the other side would fly up. You have to imagine it was a different time, and most people were still not well educated, many were illiterate. Okay? And when they saw this happen, it scared them, because they didn't have any explanation for why. So when Newton tried to explain that, he imparted something important to this ball, and when he let it go, the ball possessed it and took it towards the others, and when it struck them, it transferred this essence that he had given it, this living essence that he had given to it, and it transferred it through the others, and it's what made the ball on the other side fly off. And people looked at him and went, so you're a witch. And that was not something you wanted to be called in Newton's time, because in Newton's time, witches, well, they didn't have it so good. People pushed them off cliffs, set them on fire, or tied heavy weights to them and threw them in deep lakes. Okay? And they were like, yeah, if you drown, you weren't a witch. If you float back to the surface, or you don't die from the fire, or you survive the fall, you're a witch, and we'll find some other way to kill you. And if you just die from what we did to you, well, you weren't a witch, and you took one for the team. Thanks. It was a really weird time. Okay? And so when Newton did this, they're like, you're a witch. And he's like, no, do it for yourself. They're like, hell no. I'm not touching that thing. You're the witch, not me. Okay? And so there was this big controversy about how this worked, and he tried to explain it, but at that time, nobody had ever really been able to explain or quantify or measure this idea of energy. That was magic. Okay? And magic was the realm of witches, and it was not good. Okay? So we know now, very simply, that he did work. He said, I imparted some essence to this. That was his mistake. but there wasn't any other way to describe it at the time. The words work and energy wasn't even around, it wasn't even a concept, and work meant digging a hole or something like that. So okay, when he explained it, it sounded magic instead of physical. Right? And so he does work, and then when he lets it go, the potential energy of that ball is converted to kinetic, and when it hits the others, it's a perfectly elastic collision, and all of the energy gets transferred through them to the last one. Since there's nothing to stop the last one, it swings out to about the same height as the initial one was dropped from. Okay? And it goes back and forth. Eventually it loses enough energy to sound that it stops, but it's still an example of transference and conversion of energy. Okay? All right. Everybody okay with that? Okay, so there was a lot of different explanations for why this worked. There was like this living force, and there was like vis viva, which is like the Latin term for basically kind of the same thing, some living force that you're doing. Okay, it sounds like something out of Star Wars, but it's not. But again, it looked like magic to people, and that didn't sit well. Okay, so Newton actually spent quite a bit of time locked up by the church, actually, okay, for heresy, and so he eventually was able to explain himself and not be in jail anymore. Okay? Happened to a lot of scientists of the day who were actually very devout Catholics. It was kind of a weird time. Okay? Obviously the church is more forward thinking now, as our Pope actually has a degree in chemistry, so yeah, he's kind of a science guy. All right, now heat and energy. Okay? Heat is actually not a form of energy. What we call heat is actually thermal energy. Heat is a transfer of thermal energy. So when I feel heat from something, it's because it's transferring thermal energy to me. Okay? Heat is similar to work. Work is a transfer of mechanical energy. So when I do work on something, it gains mechanical energy. If I do heat on something, I know that sounds weird, but it's kind of the same thing, okay? Then that means I'm transferring thermal energy to that object. Or if I feel heat coming off of something, it's a transfer of thermal energy. So it's a bit of a misnomer. It's one of those words we don't use correctly in everyday life, okay? Heat is actually not a form of energy. And it's so ingrained that you'll even find that I do that from time to time, okay? Heat is not a form of energy. Heat is a transfer of thermal energy. And work is a transfer of mechanical energy. So they're similar in that way. They're both transfers of energy. They just transfer different kinds. Okay, so this idea of this ability of something to transfer without us being able to measure it or things like that, or feel it as it happened, was very intriguing to a lot of scientists. Okay, and in about the mid 1700s or so, Joseph Black did this like no-brainer experiment. Okay, he found that if you placed a cup of when you placed a cold object in a cup of hot water, the cold object got hotter. True story. Okay, now for you or I, and even people at the time, it's like, duh. Okay, of course it gets hotter. But what Black was trying to do was he was trying to explain why it happened. Okay, obviously something was moving between the hot and the cold object, and not the other way around. Okay, yes, the hot water gets colder, but you can't transfer coldness. Okay, and that might seem weird too, because it sometimes feels like we can. Okay, you can only transfer what you have. Okay, you can't transfer what you don't have. If you're cold, it's because of a lack of energy. I can't transfer a lack of something to someone else. It's not like money. Okay, debt. Okay, it's energy, so it doesn't work that way. But I can transfer heat if I have more of it. Okay, it's like if someone's hypothermic, what are you supposed to do with them? Warm them up. How do you do that? Right, or you, right? You just put yourself around them, okay? And you can transfer your own heat, okay? Sometimes you can feel that, like some people radiate heat, okay? They're just naturally kind of hotter. all right? And if you stand next to somebody and they just worked out or something, sometimes you can feel the heat coming off of them. It's because they're hotter than you, and not in that way, but like temperature hotter than you, okay? And so the energy moves from one place, from the hot to the cold. They don't get colder because you're standing next to them. You don't transfer your coldness to them, okay? But they'll transfer their heat to you. And I just said heat, and I mean thermal energy to you. Okay? All right, so based on this, Joseph Black came up with one of the principles of thermodynamics, the second law of thermodynamics, in fact. Okay? The first law of thermodynamics is the law of conservation of energy. Energy can't be created and it can't be destroyed. That's the first law of thermodynamics. But the second law of thermodynamics says that energy always flows from a more energetic object to a less energetic object. So if we're talking thermal energy, hot to cold. Okay? Does that make sense to everybody? All right. And so that transfer of thermal energy was called heat. So make sure that that's underlined because that's your definition of heat. And make sure you've got this somewhere, okay? The definition of work. Okay, so kind of during all of this, there were different ideas about how people knew that energy could do this, that it could go from hot to cold, but they didn't understand how. Okay, because there were ways to slow it down. Okay, there were ways to kind of almost capture it and make it do stuff, but they couldn't really explain why because there wasn't any change in mass. Okay, the hot object that you put in the cup or the cold object that you put in the cup of hot water didn't get heavier, so there wasn't any matter being exchanged. The object gained energy, but it didn't get bigger, heavier, or anything like that. So it was very hard to explain how energy worked because it wasn't a material. Okay? And so the Greeks had this idea way back when, that whole atom thing, remember Democritus and came up with the atoms? Okay? That could also explain how heat is transferred. If all matter is made of tiny atoms, okay, and they're always moving, and they move faster if they have more energy, then transfer of energy can be explained by atoms running into each other, which is actually what happens. Okay? When we're talking about energy transfer by conduction or convection or mechanical, like collision kind of transfers, okay, that's what we're looking at. Okay? Is energy is transferred in that way. All right? Does that make sense? Okay, so the whole atom idea could explain that. The problem was everybody had dismissed the atom idea. Okay, this is still the 1700s, right? It's, Dalton's kind of just doing his experiments here. Atomic theory is not a thing really yet. Okay, so what people said was mostly that heat is this invisible fluid. It's always convenient when it's invisible. Okay, so it's this invisible fluid that can flow between objects because energy does flow. It does seem like a fluid when it does its thing. Okay, but it's not. It's not an invisible fluid. There's no magic, to it. It just happens. It's the movement of particles. Okay, and the particles can transfer their energy, either mechanical, okay, or thermal, to each other by colliding. Okay. Now, there is a relationship between heat and mechanical energy. That is, they can produce each other. It's far more common to have mechanical energy produce heat than the other way around, but it can happen. Okay? So Benjamin Thompson, who for some reason later changed his name to Count Rumford, I don't know, seemed like Ben Thompson seemed like a good name, but whatever. Okay? He became the Minister of War in Bavaria, and his job was to supervise the manufacture of cannons. And to make a cannon, you have a big lump of metal, and then you have a crew of people who are basically running a big drill. Okay? And by a big drill, I mean it looks kind of like a small post hole auger. Okay? That you would use to drill a hole for ice fishing or drill a hole to put a post or a piling down. Okay? So, something with a big drill bit about this big. And they would all manually operate this drill. Okay? They would crank it, or they'd hook it up to a horse, and the horse would run it on a pulley, or whatever, but the thing would crank. And what they found was a lot of heat was generated by this process, the process of boring out the lump of metal to make a cannon. So much so that they would fill a tea kettle with water and put it on the cannon while it was drilled out. And after a short time, the water would boil and they could have tea. Hence the invention of the coffee break. Not really, but maybe. Okay? So they could actually make a kettle of water boil on top of the cannon. Now, everybody knew it takes energy to boil water. Okay? And of course they knew that you don't touch the cannon after you've been drilling it. You don't touch the cannon's really hot. Okay? Workplace safety. Not that that was a thing then, but you don't touch the cannon. It's hot enough to boil water. Well, if it takes energy to boil water, or something like that, then where is that coming from? How is it getting to the cannon? Why is the cannon getting hot? Okay? And people are like, well, because the drill is moving. Okay, the drill is moving because of the people. And the people are getting their energy from their food. So it's another example of that Inuit blanket toss kind of thing that we talked about. Okay? It's these transfers and conversions of energy. But the mechanical energy of the moving drill bit was being turned into heat because of all the friction. Okay? It would grind and grind and grind, and it would get hot. Okay? If you doubt that it'll get hot, if mom or dad has a drill at home, just drill a hole in a piece of wood and touch the bit carefully. Okay? It'll be hot. Okay? There's a lot of friction when you drill something out. Okay? All right. A little bit later on, okay, so Rumford suggested that heat could be manufactured by the motion of the workers, and he was the first to realize that heat and mechanical energy were related. Then Thomas Young came along, okay, and he linked mechanical energy to this idea of kinetic and potential energy of moving objects that Leibniz had come up with years and years ago, okay, and that came, from there came our definition of energy, okay, that it was the ability or capacity to do work, okay, energy is the ability to do work. Well, work is a transfer of energy. Okay, so they're tied together in that way. Okay, now, Joule. Joule is super important. You can always tell somebody is super important if they have a unit named after them. Okay, the units for force are newtons. The units for energy are joules. You don't generally get the unit for something named after you unless you've had some kind of major contribution. All right, so we'll get to Joule here, but first, Sadi Carnot, who was a French engineer, okay, did these experiments that could transform heat into mechanical energy, the opposite of what Rumford had found with his workers. They were converting mechanical into heat. Okay, but Carnot figured, you know what, you can go the other way. Okay? You can make heat turn into mechanical energy, right? And so he found that you could only do that when thermal energy flowed from a hot object to a cold object. So what you had to do was harness the flow of thermal energy as it went from hot to cold. You could get something in the middle, okay? Between that transfer, you could make that energy do work, because that's what energy is, the ability to do work. So if you could get something in the middle of that, you could get it to do some mechanical work for you. Right? So he came up with this idea of the heat engine, but we'll get to that actually a little bit later. Okay? Joule was the first person to show that mechanical energy consisted of two parts, and that potential energy was a form of energy, and that it could do work. Okay? And he did it with these two fairly simple experiments. Okay? So his first experiment, which was the simplest, involved two blocks, a falling block and a stationary block. Okay, so the falling block was kind of on a pendulum, so you could swing it out and away. Okay, if you take a block and you swing it out and up, what have you done? Work. You've given it now potential energy, because it could fall. If you let it go, it'll fall. So it has potential energy. Okay? And what people were not agreeing with at that time was that potential energy was a thing. Only moving objects could do work, so only moving objects had energy. There wasn't any way to kind of prove that potential energy was a thing. So what he did is he just moved the block away, and on the stationary block, he put a thermometer in it. Okay? And when he released the falling block came crashing down and smashed into the stationary block. And the temperature of the stationary block went up. Okay? There's no other sources of energy other than the falling block, and the only place it could have got its energy from was from being lifted up and away from the first block. Okay? So it proved and showed quantitatively that potential energy was a form of energy and could be converted to kinetic, which could then do work. Okay? He did a similar thing with this setup, okay, where he had these masses on a pulley and they were tied to the lid of this jar, which could spin. So when the masses fell, it would spin this thing really quickly, and it would spin these blades inside, and the air inside would get warmer because the blades would be spinning through the air, and there'd be air resistance and friction, and the temperature of the thing would go up. Okay? So again, proving those masses had potential energy. When I let them go, they fell, converted it to kinetic, which could be shown there. So he's basically just showing that energy is real. It can be transformed and transferred, okay, by objects. All right, I would like you guys, using your notes, to answer these questions here. So 2, 3, 4, 6, and 9, okay, and 10. As well as 12, 13, and 14. Okay? Give you guys a bit of time on that, and then we'll go through them together. Okay, let's go through these here. So for question number 2, okay, we're looking at the inventor, right, or the scientist here described their invention, the type of energy the inventor was able to produce, and how it was produced. Okay, so Ørsted had the current carrying wire and the compass. Okay, so he produced magnetic energy from electricity. Essentially, he produced the first electromagnet. Okay, he was able to impart magnetic properties to something that was not inherently magnetic. Okay, so he made the first electromagnet, which then was later turned into things like transmitters and receivers and basically the start of radio. Okay. Faraday did the opposite. He converted magnetic energy into electrical energy by forcing electrons to move by repelling them or pushing them with a magnet. Okay. Seebeck made the first thermocouple, okay, where he converted heat directly into electrical energy. What about Edison? We kind of skipped over him. What did Thomas Edison make? He's actually the whole reason that the symbol for a great idea is a what? A light bulb. Okay? His great idea was the light bulb, which converted electrical energy into heat and then into light. Because the first light bulbs were what we call incandescent light bulbs. They're the ones with the tungsten filament in the middle. Okay? They're highly inefficient, and you probably don't even have any in your house anymore. Okay? Because they made light from heat. They were very, very inefficient. They were also awesome at the time because they took night and turned it into day, okay? Which was a big improvement over candles and lamps. But at the same time, they did produce a lot of heat. They still do if they're used, which is why generally we have replaced them with LED. Okay? I can replace a 60-watt incandescent bulb. That means that bulb uses 60 joules of energy per second. That's the Thomas Edison type, 60 joules per second, with a 4-watt LED. Okay? If you turn on an incandescent bulb and it's on for more than 5 seconds, you cannot touch it. It'll be that hot. You can have an LED bulb on for hours and just reach up and unscrew the thing. Okay? They don't get hot. Okay? Not like an incandescent bulb. Okay? It's actually why if you've ever gone inside of taken a light fixture down, okay, especially ones that are flush with the ceiling, they actually have a piece of insulation with foil on it. It reflects the heat so it doesn't start a fire in your ceiling, okay, if you have incandescent bulbs. Okay, and what did Volta discover? He made the first what? Right, he made the first battery, like the first essentially dry cell battery. Okay? He converted chemical energy into electrical energy. He proved you could store it, basically. All right. So what's a practical use of the invention today? Well, Orsted, electromagnets, picking metal things up, or radios, like transmitting and receiving information. Okay, Faraday, well, generation of electricity, so we still use it for that. Okay, Seebeck, we said thermocouples can be used to do regenerative braking. Okay, used in like hybrid vehicles or electric vehicles, and also for circuit breakers. Edison, well, we don't really use his direct invention. We use the descendant of it, okay, but still used to light up dark places. Okay, and Volta, still used to power mobile devices. All right, number 4, what's the difference between nuclear fusion and nuclear fission? So fission does what with an atom? Splits it. Fusion forces 2 atoms or more than that together. Okay, so they're different in that one puts them together and one takes them apart, but they're similar in that they both harness, or release rather, the energy contained within the nucleus of the atom. If the nucleus of the atom is altered, then the energy in it is released. Okay, what's the modern theory of the source of energy from the sun? Well, we just talked about it. It's nuclear fission or fusion? Fusion. Okay? The sun is powered by nuclear fusion. Its immense gravity and immense mass essentially crushes hydrogen atoms together to form helium atoms, okay, and releases that energy. Okay, and then describe the contributions of the following people. Okay, Sadi Carnot. Well, he was the one who discovered that mechanical energy or heat could be converted to mechanical energy. Okay, Young, we talked about, it says James Young here, but it's actually Thomas Young. And he was back here. Not that far. Young, he was right here. Okay, Thomas Young, okay, linked mechanical energy to this idea of it being made of both kinetic and potential. Okay, and then looking at Black. Okay, Black was the one who discovered that energy flows from high energy objects to low energy objects, or hot to cold. Okay, and Rumford discovered that you could turn mechanical energy into heat. All right, for number 10, explain how Joule proved that heat could be produced from potential energy. In your description, state the manipulated variable, a responding variable. Describe how a change in the manipulated variable affected the responding variable. Okay, so if we go back to Joule's experiment with the falling block. Okay, the manipulated variable in that experiment was the height the block was dropped from. The responding variable would be the energy change of the stationary block, the change in temperature of the stationary block. Okay, if he dropped the block from higher, the temperature increase would be greater. Okay? That's essentially all they wanted you to do for that question, describe how his experiment worked. Okay, number 12, in the following situations, identify the major form of energy involved. So an antacid tablet is placed in a glass of water and the tablet starts to bubble. Anybody ever seen Alka-Seltzer? Okay? You drop it, it's like plop, plop, fizz, fizz. Okay, it just gets all fizzy. Right? What kind of energy would that be? What do bubbles usually indicate? A chemical change, yeah. Okay, so that's chemical energy. It's actually it's a chemical reaction between the base essentially that's in the antacid tablet. Okay, fluorescent dial on a wristwatch glows at night. Okay, this is probably something that's becoming a generation gap type of question with the advent of smartwatches. But older watches used to have little bits on them that were fluorescent. That means if you were out in the light, they would absorb the light energy, and when you went into the dark, they would glow for a short period of time as they released that stored energy. We actually talked about this the very first day of class. It's also how photosynthesis works. Okay, they absorb the energy from the light. Okay, it makes the electrons jump to a higher energy level, and then when you get in the dark, those electrons fall down to lower energy levels and release it as light. Okay, so it's also a form of chemical energy. Okay, and it's light energy mostly there. Okay, downhill skier begins to ski down the slope with increasing speed. Okay, so if they're on the top of the slope and they're skiing, they would have both potential and mechanical, yes. So those two things, there's one energy we're missing. Potential and something equal kinetic, or equal, I said, potential and kinetic equal mechanical. Okay, so he would have both because he's at the top of the hill where he still have potential and skiing, so he's moving, so he has kinetic, which means he also has mechanical energy. Okay, tingling sensation is felt on the tongue when it is touched to the terminals of a 9-volt battery. You guys brought that up the other day, okay, that you can zap your tongue if you put it between the terminals of a 9-volt battery. I can't even imagine what still uses a 9-volt battery anymore, but okay, that would be electrical energy. E, the inside of a car gets extremely warm if the car is left in the sunshine. Sunshine turns into what kind of energy? Thermal energy. Okay, a seagull lifts a clam high above the beach. And kinetic, yeah. Okay, both. Because it's above the beach and seagulls don't generally hover. Right? So it would be moving. All right, and a compass needle is held over the surface of the earth and points north. Okay, so that would be magnetic energy for that one. All right, for 13, describe an appliance or a machine that for its operation requires the following forms of energy. Okay, chemicals easy. Anything you put what in? Gas. Anything you put gas in requires chemical energy. Even lighting a candle is chemical energy. Okay, lighting a campfire is chemical energy. Okay, light. What might require light to work? That produces light. What requires light to work?
Solar panel?
Yeah, anything that's plugged into a solar panel. Okay, if you have a calculator with a solar panel on it, okay, your calculator needs light to work. Okay, heat. Kettles, yeah. You're going to boil anything, you need heat for that. Okay, you're going to cook anything, you need heat for that. Okay, and it should actually say thermal energy because heat's a transfer of thermal energy. Unless you run it on the cold cycle, right? Like we always run on cold in the laundry just because it saves energy. But yeah, I mean, it could. You'd have to heat the water if you're on the hot sanitary cycle or something like that. Okay, electrical energy. That's pretty easy. Anything you plug into the wall.
Microwave.
Yeah, microwave, toaster, okay, anything like that. Hair dryer, right? Magnetic energy. Anything that would require a magnet to work. Compass. Right? It doesn't work if there's no magnetic field. Okay. Other things that require magnets? Electric motors. Okay, they are full of magnets in order to work. All right, 14. Describe an appliance or machine that produces the following forms of energy. Okay, what produces chemical energy?
I'm not sure on this, but would a microwave do that?
No, it's not going to make chemical energy, no.
A gas stove.
That uses chemical energy. We're looking for something that would make chemical energy. This is a tricky question because of the way they worded it. They're green. They make chemical energy as long as they're in the sun.
Solar panels.
Nope. But those are green. I get what you were thinking there. I meant green, the color green.
Plants?
Plants, yeah. Plants make chemical energy. They're food after all. Okay? They convert solar energy into chemical energy. Okay? And you could also say like a fuel refinery. Okay? Would be taking one form of chemical energy and turning it into another form of chemical energy.
I was going to say a pump check. It's called.
Answer the next one? Okay. Something that'll make light? A lamp? Yeah. Anything you can like flip on and the darkness goes away with? Yeah.
Okay, for B, C, and D,
Yep.
a microwave.
Yep.
It has a light bulb.
It has a light bulb in it.
And if you put a spoon in the microwave, it makes electricity.
Yeah, it's not so much that it makes electricity, it just sparks. Those are not necessarily, yeah, but
There's electricity in
it's
the
converting electrical to thermal and it's sparking. But yeah, don't put anything metal in the microwave. That was a big problem when microwave ovens first came out. People put all kinds of metal crap in there and burn them out.
Oh, wait, when people started putting their iPhones in there because it apparently charged it.
Are people that?
Well, a bunch of people made fake ads for it. That an iPhone 6 update came out where you could they would turn the microwaves into power, and then people would microwave their phones. They also said the same thing, that there was an auto water blocking thing that would detect the water and cut off the battery.
Well, you get a message if there's any moisture in the charging.
Yeah, but this was like
But
for
it
the
doesn't.
iPhone 3.
Oh, okay. Yeah. What's that?
There was a trend a long time ago where you would put like a foil ball inside a microwave to make it smooth. And it wouldn't work.
No, I wouldn't
Yeah,
work.
people thought it did.
People will believe
There's also
anything.
another reason people that you bend your phone as much as you want.
Okay, and then lastly, magnetic and electromagnet. You got bar magnet, anything that, even your cell phone makes magnetic energy. It's how it transmits and receives signals. So, all right, questions on any of those? Okay, cool. Keep those answers because that's easy quiz material or multiple choice material on a unit exam, not Wednesday's unit exam. Okay, so a word or a concept that comes up often when we're talking about energy, okay, and talking about thermodynamics is systems. Okay, systems can be classified into 3 groups. Okay, open, closed, and isolated. Okay, open systems are the most common. Right? If I have an open system, that system exchanges matter and energy with its surroundings. So all of us are open systems. Okay? When we're breathing in and out, we're exchanging matter with the environment. And we're warmer than the air we're in right now, so we're slowly transferring energy to the air. Okay? We're exchanging matter and energy with our surroundings. Everybody with me on that? Okay? So we're an open system. A closed system, okay, can only exchange matter, cannot exchange matter, but can only exchange energy. So it's something that's sealed, airtight. So if you were to, let's say, like put something in a Ziploc bag and then throw it in the freezer, okay, that would be a closed system. It would get colder because it would transfer its energy to the freezer, and the freezer would absorb it, okay, but it would not exchange any matter. Sealed it up airtight in something else. Okay, so that would be a closed system. And then there's isolated systems. Isolated systems are purely theoretical. We cannot make anything that does not exchange matter and energy with its surroundings. Okay, it is impossible to completely isolate anything. It's possible to close something and prevent the exchange of matter, but we have not made it possible to stop the exchange of energy. Okay? We can insulate something, but we cannot isolate it. Okay? So if I had like if my coffee cup, for example, okay, was an isolated system, my coffee would still be exactly the same temperature it was when I brewed it this morning. And it would stay that way forever. That'd be useful. Okay? But I have to settle for an insulated mug, okay, which is an open system. I drink out of it, okay, so it's losing matter to its surroundings, me, okay, and it exchanges energy slowly, okay, not quickly, slowly, right? It's not perfectly isolated. There's no way to perfectly isolate something against energy loss. Some small amount of energy is always going to be lost to the surroundings. It's impossible to prevent that. Okay? All right, questions on the 3 types of systems. So things you need to know here, definitely know each system. Okay, so open system exchanges matter and energy. Closed system cannot exchange matter but can exchange energy. Okay, isolated system does not exchange either one. And a system is a set of interconnected parts. Okay, now, this is something we've talked about now 3 times, okay, since I started this unit. And that is the difference between heat and work. They both transfer energy, but it's the type of energy they transfer that's different, okay? Work involves the movement of matter, okay, from one location to another, whereas heat is a transfer of thermal energy from one location to another, okay? So work is a transfer of mechanical energy, heat is a transfer of thermal energy. Okay, so it's important that we know the difference, okay? Easy to make a multiple choice or even a written response item about the difference between heat and work. All right, now, first law of thermodynamics is the law of conservation. Like they say, first law of thermodynamics and the law of conservation of energy. It really should say is the law of conservation of energy. Okay? Energy can't be created, it can't be destroyed. It can, however, be converted to other forms, and it can be transferred, either gained or lost by an object or system. So you can change the energy of an object or system, but only by either adding heat or doing work. Okay? Similarly, a system can lose energy by transferring thermal energy away, heat, or doing work on something else and losing its mechanical energy to that other thing. Okay? So we can change the amount of energy a system has, but it's got to be accounted for. Changing it doesn't mean I destroyed it. Okay? Gaining it doesn't mean I created it. I got it from somewhere. If I gain energy, I got it from somewhere. Okay? Either by heat or by work. I didn't just magically go, I need more energy. And there it is. Okay? It doesn't work that way. The only way to change energy is to have it transferred to you. The only way to lose energy is to transfer it away. Okay? It is still accounted for by the law of conservation of energy. It can be converted to other forms and seem like it's been lost or destroyed, but it's never destroyed. Okay? The most common form of energy that represents a loss of energy is thermal energy. Okay? Because nothing is 100% efficient. There's always going to be some friction that's going to make heat and sound and other forms of energy that make it look like energy's been destroyed. It's not destroyed, it's lost by converting it to other forms. Okay? All right, so that's kind of the important thing. Energy can flow out of a system. Okay, so the first law of thermodynamics is highlighted here. Okay, make sure that you've got that as well. Okay, because it's very important to know the wording of that. And you can put it in your own words. Okay, might be a good idea. Okay. So in the first picture here, we're seeing that idea of thermodynamics, that energy flows from a high energy object to a low energy object, or from hot to cold, from this hot piece of metal, which you should not hold with your bare hands. That would be a very bad idea. Okay? It would flow from the metal rod into the water, okay? And the water would gain energy. The rod would lose it, and it would all be conserved. Okay? Similarly, in this situation here with like the pogo stick, okay, where you jump onto the pogo stick, what you do when you jump on it is you stretch the elastic bands or compress the spring, whichever one it operates on, okay, which represents a conversion of gravitational potential energy to kinetic energy to elastic potential energy. When you compress a spring or you stretch a rubber band, you turn your energy into elastic potential energy. Then that elastic potential energy will do work and push you away, converting it back into kinetic energy, and you can bounce along on the pogo stick, constantly converting these forms of energy into each other. Okay? So if you get that thing bouncing, will it go forever? You have to keep putting energy into it, yes? Okay? Because it's always losing some energy. It's losing it to heat, as sound, as whatever. Okay? But it's losing energy each time you do that. Okay? Everybody good with that idea? Okay, so that's the first law of thermodynamics. We need to make sure we understand how that works, okay, because it's really important. And we will talk about perpetual motion machines tomorrow, okay, after your last quiz on plants, which I will post tonight. Plants, that's what it's on.